Oh, hey, thanks, Jules. Can you guys hear me? Awesome. So should we get started? I mean, still have to, I guess I have the extra 10 minutes. Thank you. Hi, guys. 30 minutes still? All right. Okay, so let me just start by giving a little bit of a context for what we are doing with SnappyData. It's actually an open source project. And the history is that we built Gemfire, which is now Apache Geode. How many here have heard about Apache Geode or Gemfire? Okay, maybe 10%. So essentially, it's an in-memory data grid. It is all focused on transactional workloads, low latency, high availability workloads, much like Cassandra's, except in-memory was the focus, right? So primarily Wall Street, banks, and then we branched out to everything, right? So today it's being used in Southwest Airlines, runs it, a whole bunch of very high transactional, low latency systems. So as we essentially went to the market, trying to essentially get Gemfire running on top of HDFS, and lo and behold, the market said it's in-memory on top of Hadoop, and immediately people started throwing analytical workloads. So essentially, it's the realization that today we live in a world where increasingly, if you start thinking about streaming applications, the workloads tend to be mixed in nature, right? Where you have to deal with the stream, you have to deal with high write rates, you need HA characteristics, you actually need transactional characteristics. I'll explain that. So it's really, essentially SnappyData. So in some sense, takes Spark to the next level. If you want one way to think about Spark, obviously, it's a confluence of interactive streaming and batch processing, right? That's how Databricks defines it. But still the batch design center, right? So what we're trying to do is to say, can we in a way take what we built with Gemfire and sort of push it into the executor itself in Spark, right? Sort of essentially coming up with the next generation, if you may, operational database that primarily operates in main memory that also offers OLTP semantics, essentially streaming OLTP and OLAP in one, and we have a bit of innovation around probabilistic data stores. So that is what it is. So again, it was founded, it's a spin out of Pivotal. We were initially in VMware, and then Pivotal drove essentially Gemfire, and then started to think about how we build this out. We were spun out in 1/1 of last year. It's about 25 engineers, and we are essentially the investors are Pivotal, GE, and GTD Ventures. So this is the key. Mixed workloads are everywhere today, right? And what you see actually is a virtuous cycle between what happens in the stream processing layer, followed by the fact that streams are continuously emitting data that I have to write and save it into a store. So I really need high write rates into the store. And then off you go into the store, and then you essentially land up saying, I need to analyze the store, so I'm running interactive queries on the store. And then quite often what you'll end up seeing is today, right, where you might be exploring data sets and you might be creating a model and you want to inject that model back into the streaming pipeline, essentially a virtuous cycle, right? So here's a simple use case in the telco domain. So telco, if you guys have been following the telco space, given that the margins are shrinking, there is an increasing demand for use cases like location-based services, another use cases in the network optimization space. And the location-based services, which is kind of, perhaps illegal here, but if you look at out in Europe and stuff like that, a subscriber can opt in for advertisement. So based on where you are, an ad could be placed, right? So there, you'd see that there are, typically stream processing has been more about apply a rule on a small window of data and maybe I raise an alert, right? And what is increasingly happening is that can we go from stream processing to stream analytics, right? Where not only just looking at a small window, but I need to really correlate. I may need to do a join. I may need to do top K analytics. And all of a sudden, essentially, you're looking at the same kinds of optimizations that you're used to in an OLAP engine, a columnar database engine that now needs to be applied in the stream processing layer itself. Right? And that's kind of one of those interesting sort of confluences, right? Saying, hey, the stream processor design center was one. You have the columnar database that's a different design center, but they in some sense need to come together so that you can realize a richer set of analytical applications, right? So let's just go a little bit deeper. So here is what I'm showing is, stream represented as a time window, and you are essentially taking a high velocity stream and writing essentially potentially to a table that is in some sense ever growing, right? and then you may have one or more reference data tables. So for instance, in this sort of telco example, you have call data records coming in at a high rate. You might be processing it essentially by doing and sort of massaging the data, writing into this table that is essentially time series data that's perpetually growing. But you also need CRM data potentially to look at saying, okay, can I essentially look at the profile of the subscriber so that I can do efficient joins and things like that. So one of the immediate challenges there is how do I now do a join between what's happening in the stream. Now the interesting thing is that even in this domain, it's going from saying, oh, I just need typically look at the window of a few seconds to increasingly going and saying, I need to actually process the stream windows that could be an hour, even in fact for a day. And I'm essentially sliding that window every few seconds. In other words, I'm looking at data. So for instance, do I see the call drop rate, go up or down, a trend for the last hour that I'm essentially processing every 2 seconds. But to do that, to make effective decisions, I need to now join the data with other reference data, right? So you're essentially joining the stream with the historical data and potentially joining to reference data. Now the key thing is that the reference data itself could be in real time, is also getting updated through external other systems, right? So what you really need is not only do I need joins and that kind of capability along with the streams, but I also need support for fast writes, updates, exactly one semantics, and in fact HA. And if you think about it, I mean, if you have a situation where a single stream that was coming in, inside Spark landed up being distributed essentially, or either I forked the stream into multiple streams, or I just landed up doing distributed processing, you ultimately realize that to write into the store, if let's say I'm doing aggregations, right? Essentially doing counters out and writing it into the store, I actually need, in fact, I do need transaction semantics. So that becomes a very important consideration. On top of that, once I have all this data emerging, I want to turn around and have a BI tool essentially run interactive queries on this data, right? And all of a sudden, if the interactive queries are really scan-oriented, let's say I'm doing an aggregation of some sort, how do I do it at high speeds, especially when the data is coming in and I'm constantly doing high writes into these tables, right? So you not only do you need the ability to support high-speed scans and aggregations, you also need high concurrency support. In other words, can I get a whole bunch of users that could either be exploring data, but more importantly, applications, online applications that are also can run queries on this if you may real-time store. And on top of that, you also may need point lookups. So what you really see is that you need all the characteristics that you'd see in a high-scale, OLTP-like store like a Cassandra or a Gemfire. You also need the capabilities that you'd see in a very modern column-oriented MPP database. And of course, you need optimizations in streaming solutions, right? Because one of the interesting things is that if I'm essentially joining a window, let's say, which is an hour long, and I'm incrementally sort of sliding that window every 2 seconds, can I do incremental processing? Incremental processing becomes, rather simple. Incremental processing becomes rather simple if I'm doing a sum, right? Hopefully this shows up. All right. But incremental processing becomes rather difficult if I'm doing, let's say, a median or some operation that requires me to essentially operate on that whole window, right? So those are interesting challenges. So essentially, when it comes to mixed workloads, the point is that the design center is really also a confluence of what happens in a columnar database, what happens in a row store. And if I'm running interactive aggregation kind of queries, you might have to think about, hey, how do I schedule, essentially something that's going to suck up all my CPU when low latency operations are going on concurrently, right? On top of that, if I'm dealing with a stream that is sort of infinitely giving me more data if it's time series, so your data volumes are very, very high, right? In a whole bunch of domains. If, let's say, if you're dealing with IoT or industrial IoT, you're accumulating terabytes and terabytes of data on a single day. So how do I essentially do interactive querying on such a large volume? So increasingly, you would see that there is a momentum towards saying, can I have probabilistic data structures, essentially data structures that can synthesize something very, very small, keep it in main memory, on which I can interactively ask interesting questions. So today, if you look at, I don't know why it's not. All right, I just had to do this, I guess. So today, most of, if you look at the standard answer, it's all about Lambda, right? And I'm not going to go into Lambda, but it's about taking new data as it's emerging, writing it to a speed layer, which is some sort of Storm, Spark streaming combined with a store that operates and offers you linear scalability like Cassandra. And then you also write it to a batch layer. And then it's up to the application to, in some sense, do the stitching between all these systems. So our take is that Lambda, I mean, our focus is in the streaming and the interactive layer. But Lambda to us is rather very complex, right? It's complex because in some sense you have to learn and master multiple products, different data models. You have to tune these different products. And the challenge actually lies, when you actually go into production, right? And all of a sudden, if I have new requirements coming in that causes my schema or my data properties to change, and all of a sudden I have to now touch the streaming layer, the streaming app. I have to touch maybe my Cassandra store because my structure has changed. And of course, then if I'm running SQL on Hadoop, again, that application also has to change. So it's just a series of changes requiring, in some sense, an army of developers to always be on it. And then it's wasted resources. In fact, it's much slower. One of the things that is not really talked about much is the amount of copying that happens in these modern day clustered systems, especially the ones based on Java, right? And in big data analytics, I mean, the single biggest cost, if you actually analyze, you're paying is the amount of copying that's going on. And if you look at the graphic on the right, it's simply depicting a simple clustered store that is taking a piece of data that's coming in on the network and replicating it synchronously on another node and acknowledging it back. And you're talking about 7 or 8 copies going on, let alone potentially inside the JVM, the from and the to spaces. The guys who looked at JVMs closely, you know that there's a lot more copying going on, right? So now, similarly, if you now look at the common architecture with, let's say, Spark streaming, and I'm essentially using a NoSQL store on the back end, that also is pretty inefficient. Now, it's fairly efficient today if my streaming application is rather very straightforward. In other words, I'm just taking my stream, doing some basic processing just on the window, and I'm continuously writing, let's say, into Cassandra. But then if I want to turn around and say, can I ask an analytical question? Can I ask an insightful question on the data? You have no choice, but you're left to saying, hey, let me run that query on Spark. And all of a sudden, I mean, those of you who paid close attention to these connectors, you can only sort of push down predicates, you push down projections. But then, if I'm running an aggregation query, all of a sudden, I'm having millions of data points that are essentially coming out of this NoSQL store into Spark, lots of copying, serialization, deserialization going on. And also Spark, I mean, those of you who followed sort of Spark's tungsten optimizations and the vectorization optimizations, you lose a lot of those nice, good richness because of the data format changes that are going on. So the question really is, can we simplify and optimize? So that's really our proposition with SnappyData. So in a nutshell, again, SnappyData is a single cluster. Rather than sort of saying, here is a Spark cluster and here is a data store cluster, we're taking the data store and fusing it in Spark. So one way to think about it is that we're taking Spark from being a pure computational engine and in some sense turning it also into an operational database, right? Sort of making Spark much more applicable to a lot of these real-time mixed workload scenarios, right? So Gemfire, which has a real-time, low latency, high availability design center fused with Spark, to us, which is fundamentally a very high throughput batch-oriented design center, right? So Spark, I mean, a lot of folks, HA is not to be confused with Spark's failure detection and failure recovery models, right? HA is all about saying if there is a failure, the system and the cluster is able to detect failures in milliseconds, and it's able to sort of fail over client connections within that small period of time. Imagine you have a real-time application that's connected and end users are connected to the system. How can I essentially detect and switch over very, very quickly? So the HA semantics truly requires you to have a true distributed system underneath the covers, right? So in a way, what we're saying is that we're turning Spark from a computational engine to what it looks like here, which is we have embedded essentially an in-memory store. It's a hybrid in-memory store, so it has row-oriented storage, much like what you would expect in an OLTP engine. It has column-oriented storage, very similar to how exactly Spark essentially manages column-oriented data, if you take a data frame and you do a cache operation in Spark, it essentially creates column-oriented structures, right? I mean, it essentially creates batches of columns, and it does compression. So we do the exact same thing, right? So when it comes to column-oriented data, we manage it the way Spark manages it. The data is in fact mutable, so you can essentially index on these data structures, mutate it, run transactions on it. I mean, the architecture fundamentally is a bit different than Spark in the sense that these executors now are actually coupled to one another more closely than it is in Spark. Spark essentially has a master and a whole bunch of worker strategy. In our world, given our high availability semantics, we make sure that the executors can in fact talk to one another so that we can detect failures very, very quickly. So it's like saying that here is a cluster, it's a database cluster that's up and running, and Spark executors are running in the same process space where we manage our data sets. But we also allow Spark clusters to talk to this database, right? So you can have an external Spark cluster that's running in Yarn, Mesos, what have you, which is purely a computational grid, and you can still work with sort of SnappyData, much like using connectors. And even these connectors really fast because of how we parallelly process data, given that the data structures are very similar underneath the covers. All right, so yeah, so at a high level, again, it looks like this. I mean, things in blue is Spark, things in sort of the boxes in kind of light green is what we added to Spark, right? So you can, so the nice, beautiful thing here is that the Spark ecosystem is so rich, right? Which is something we didn't want to work on, right? The ability to say, hey, can I essentially work with HDFS, cleanly S3, I can work with Cassandra. I mean, all sorts of data sources. In a way, I can sort of federate data from any of these data sources relatively very, simple way. The transformation APIs, just really amazing, really awesome amount of richness there, right? And sort of the SQL thing, in Spark SQL, it's all about selects. So we essentially give, obviously, given that we do mutations, we had to make sure that you can do inserts, updates, we support keys, you support constraints, all the stuff that you'd expect from an SQL engine. The catalog itself is also fused together, right? All right, so let me just go a bit into the architecture of the store. I have no idea how much time I have. Did I elapse already 30 minutes? 10? Oh boy. All right, I'm going to skip quite a bit here. All right, so essentially what you'd expect from a store, right, which is in Spark land, which is any of the tables that you have, obviously you can come in through SQL and access it, or the tables can actually be visible as simply as data frames also, all right. So row tables allows you to do random writes. You can have key-based lookups very fast if I want to do very low latency selective operations, right? What you'd expect from a NoSQL-like store. So you can essentially have an inbound ingestion stream being processed where I'm writing something to row tables. Some stuff goes into essentially if the data is ever increasing, you can write into column tables. And the way we support mutability in column tables is that we have a row buffer, what you would expect in, for those of you know MPP databases. You have a row delta buffer that essentially is where we initially do the writes, and periodically the writes are transferred into the column table. I'll touch on this technology called, we call it the synopsis data engine. We've embedded probabilistic data structures into the SQL engine, into our engine itself, such that it's visible to general purpose SQL applications. API is pretty much Spark compatible. If you're familiar with the Spark data source API, it's pretty much acts as another data source. And we have extensions on the Spark session API so that you can do updates and deletes and those kinds of operations. All right. If you're doing SQL, when it comes to selects, our syntax is mostly what Spark SQL is with a few extensions, so that we support cursors and things like that. And of course, when it comes to SQL, you can obviously come through JDBC, and we support all the SQL syntax of updates, deletes, and all what have you. The extensions on the SQL side are also offered through Spark options, right? So if you look at the DDL, we can do things like, hey, can I co-locate multiple tables together? Can I partition it on a custom way? Can I partition by primary key basis? Redundancy essentially allows us to say that, hey, if I create a piece of data, I can have one or more synchronous copies inside a cluster, and I can have asynchronous copies across, let's say, WAN boundaries, right? So things like that, right? Pretty straightforward. We also added a few extensions to Spark streaming to make stream processing more appealing to SQL developers, right? So that, for instance, one of the things we offer is, so you can do essentially declaratively, you can define streams using SQL, using create stream table. This is based on a project that Intel did. As structured streaming emerges and becomes more like 1.0, we essentially plan to integrate with that. I'll just skip this. Essentially allow you to register what's called as continuous queries, and the continuous queries will essentially run as my stream is emitting data, right? And then you can easily take the results of a continuous query and essentially write it into our column or row store very, very easily. So this is what I touched on, how we, this is going into details for how we support updates and deletes. So I'll touch a little bit on sort of the statistical data structures, right? So like I said, one of the challenges we have with this high velocity streams is that, hey, my data is continuously growing. How am I going to run a query if my data is going to be 10 or 20 terabytes and I'm claiming that I can give you interactive speeds? It's simply not possible, right? Unless until I have tens of thousands of cores available. So the idea here is to really take, understand data, characteristics of distribution patterns, for instance, characteristics of data, and create essentially these data structures, right? Like sketches and samples. Sampling is the simplest way to think about it. But if I create these data structures, can I essentially run a SQL query? And obviously the trade-off here is accuracy, right? In other words, I can give you a 100% correct answer. I'll give you an answer. It's, the question is, can I use algorithms to tell you how good my answer is, right? That's the key thing here. And the nice thing is that, if you look at the graphic on the right, it gives you this thing saying if I'm visualizing big data sets, how can you tell a difference between a 100% correct answer and a 90% correct answer? You can't really tell it. And I'm going to skip all this, right? The probabilistic details. We use things like count min sketches. We support count min sketches to work on time series data. We do stratified sampling, but we also support not just static samples, we support dynamic. In other words, if I have a stream coming in, can I essentially build a stratified sample over time also? Okay. There are a bunch of other optimizations. So let me just see if I can show you guys a quick demo, assuming it's still, how many, do I have like a few minutes? 5 minutes, okay, excellent. All right. Maybe I'll just stop in a minute or two and then take some questions. Essentially what this is showing is a simple Zeppelin-based notebook where we're comparing essentially SnappyData's in-memory performance to Spark caching and also to Cassandra. I was going to actually run it. I don't have the time. This is actually going to be visible through our blogs on our site. The project is open source, so anybody can download it, try it out. It's pretty simple, right? So what I'm doing is I'm taking 100 million records in a 2-column table. It's running on AWS on a compute instance with 4 cores. And we're simply running an aggregation query that says, hey, give me the geo and an average bid. And I'm grouping. And we're saying, hey, how fast does it run, right? Based using, so if, I'm not going to run on the Spark side, but if you look at on the Snappy side, if I run this thing, oh, sorry, not this one. Not the right one. So, what happens is, I ran it and, averaged the query time scanning 100 million records and doing a group by took about 190 milliseconds. The same thing on Spark Cache would take about 2.7, 2.8 seconds. And the reason why we see that optimization is some of those vectorization changes that have gone to support Parquet and Spark, not yet there for Spark caching and things like that. So there are a number of optimizations because the store is so embedded, we could capitalize on, right, in Spark. And what this is showing now is that, hey, I'm creating a sample table on that same table, that's 100 million. And if you see this, even though the count is 100 million estimated, the real count is only about 1 million. It's a 1% sample, and I can simply run the same query on the sample, and it literally took only 40 milliseconds. In fact, a lot of this time is because of Zeppelin and other things going on. Anyway, so hopefully that gives you guys a sense for what we are up to. Are there any questions?
Yeah, in terms of your query optimizer and SQL parser, what have you done? Invented your own or borrowed?
We had our own parser in the Gemfire world, right? So we actually blend what we have done with the Catalyst engine. I mean, essentially, Catalyst is pretty extensible. That's a great part about Catalyst. So we essentially extended and used those extensions to do what we needed to do.
I see. Okay.
Any other question? Right here.
One of the biggest challenges I'd faced with a streaming solution was, accessing global state in your stream, just like you were talking about earlier. And there, a lot of approaches that solve that will partition your stream, and then you have some local in-memory store on every partition, and that's how you handle that. Is there any sort of optimization going on underneath the covers to delineate between kind of stream partition level optimizations versus needing to access the global state?
That's a great question. That's a great question. Yes, so what we do is our design is very driven by saying do the least amount of shuffling in such systems as possible. So one of the things we do is, let's say you have a Kafka engine that is actually pumping into Spark, which is pumping into our store. We pay attention to how Kafka is partitioned. And to greatest extent possible, we would say that, hey, my partitioning is going to rely on my parent's partitioning. And if you can detect that it is a Kafka partition, then we would just retain that partitioning, unless until the user said, no, I do want to partition it this way. So we essentially save on any of that shuffling cost. Gives us huge improvements. Yeah. One other?
I was wondering if there is any user access control here, or maybe if you have more than a few people in the team, perhaps you want to have some kind of just read-only access for certain tables, and then have some user space.
That's
where they
correct.
can play around.
Right. It's also, even though it is based on Spark, it's also a SQL database, right? I mean, it's like Spark SQL. So when you come in through SQL, there's absolute access control, much like what you would expect from a SQL database. One last, maybe? Okay.
Going once, going twice. Anybody from here? This file is neglected. You had a question? Okay, I'll just run down.
Are you able to keep up with the updates in Spark versions? Is there any time lag there?
So the question is, are we able to keep up with the update rates in Spark?
Versions, yeah. Are you on 2.1?
Oh, yeah. Okay, thank you. Yes. So we have a lag right now of about a few months. Hopefully, we will retain that. So right now, we are working on releasing a product with Spark 2.1, which should get released in about a couple of months, a month or so. Yeah. So we don't know how that's going to pan out in the future, because there are a number of things where we're extending some of the internal stuff to do what we need to do, right? So we're trying to figure out, saying, hey, is there a way we can contribute it back? I mean, a lot of the changes we've done are sort of kind of tied to how Gemfire works. So it's a bit difficult to say, hey, can we contribute? But we are attempting to do that. So hopefully that works out. It is an open source Apache V2 license project, though. So okay, thank you.
Okay, give a big hand to SnappyData.